need to proceed to the last talk of the session. So the title is Optimized Item Selection to Boost Exploration for Recommender Systems. And I believe the speaker is Bernard Kleynhans. So can you please pass the video? Thank you.
Today, I will be presenting our paper titled Optimized Item Selection to Boost Exploration for Recommender Systems. My co-authors and I are members of the AI Center of Excellence within Fidelity Investments and are happy to present our work that integrates modern recommender systems and classical discrete optimization techniques here today. For the presentation itself, I'm accompanied by Wang, who will present the second half of our talk. I will start by providing a brief introduction and outlining the problem definition. Subsequently, I'll describe two of the main contributions made by the paper, namely solving the item selection problem, or ISP, and a warm start procedure. At that point, I will hand over to Xin, who will go over some numerical experiments and conclude the presentation. As an introduction, I will unpack the title of the paper itself. First, a few words about recommender systems. Although recommender systems have become central to our daily lives, building recommender systems with limited or no available training data remains a common challenge. In the classical recommender system setting, we have a set of users and a set of items from which top K items are shown to a user. The items are generally selected to be those that a user is most likely to engage with, but different rewards such as revenue or sales conversion can also be used. Notice, however, that there is an a priori decision to determine the universe of items that can be recommended. How to select this set of items for a new recommender system is the central question we tackle in this paper. To optimize the item selection, we formulate a new combinatorial optimization problem to generate optimized item selections for experimentation and refer to this as the item selection problem. The approach integrates techniques from discrete optimization, unsupervised clustering, and latent text embeddings. And the goal of the multi-level optimization approach is to minimize the cardinality of the item universe while maximizing the item diversity. That is, we want to select the smallest set of items that we can while maximizing the diversity of the selected items. Why do we do this? We do this to boost exploration or learning when building a new recommender system with limited or no data. Specifically, by minimizing the cardinality, we reduce the experimentation time window and mitigate undesired user experience and business impacts of randomized experimentation. The whole aim of recommender systems is to provide personalized experiences that are tailored to user preferences, so we want to minimize purely random recommendations. Furthermore, we propose a simple warm start procedure based on item-to-item similarity, which is boosted by maximizing the diversity of selected items. The warm start procedure is simply a way of transfer learnings from items where we now have some data to items where there's still limited or no data. Our hybrid approach serves as an integration block between modern recommender systems and classical discrete optimization techniques. To bring that all together, the problem definition can be stated as follows. Given a set of items, the goal of the item selection problem is to find the minimum subset S that covers a set of labels within each label category, while maximizing the diversity of the selection in the latent embedding space of items. To make that more concrete, consider the following illustrative example based on the movie recommender systems. I is the available movie titles to be recommended. S could be the subset of movie titles that will be included in experimentation and that we will collect data on. C is the categories of interest. This could be based on any item metadata, and in this example could be attributes like language, genre, or producer. L_C is then the individual labels associated with the different categories. For genre, we could have action, comedy, horror, etc. And EI is the latent representation of each item that can be based on text data, such as synopses and movie reviews, or even image data, such as movie cover art. At this point, I'd like to take a step back and show how this fits into a recommender system framework. For this new system, we start by solving the ISP and getting a subset of items to include in experimentation. Next, we perform random experimentation and collect training data for a subset of items S. Using the collected data, we train a model. And next, we use a warm start procedure to augment the trained model to include additional items that were not included in the randomized experimentation stage. We can then use this model to start generating personalized recommendations from which we collect more data that can be used in model training, and so the process continues. In the paper, we focus on the ISP and warm start, with the other components being generic recommender system aspects that can have orthogonal approaches. For example, for training the model, any state-of-the-art recommender system algorithm from factorization machines to neural collaborative filtering could also be considered. In the next few slides, I'll describe the approach for solving the ISP in some detail and then provide an overview of the warm start procedure. As mentioned in the introduction, solving the ISP is an instance of multi-objective optimization, and our approach is closely related to the classical set covering problem, which we embed in a multi-level optimization framework. It consists of 3 levels: finding the minimum subset size, maximizing diversity, and maximizing coverage within a fixed bound. To minimize the subset size, we use a standard covering formulation to select a subset of items that cover all predefined labels. Here we let M be the incident matrix, where rows correspond to all predefined labels and columns correspond to the set of items. We let M underscore Li be 1 if item I has label L from one of the label categories and 0 otherwise. We let xi be the binary variable denoting whether item I is included in the selection or not, and let c represent the unit cost vector. Then formulating the unit cost item selection problem, which we call P unicost, is straightforward as shown on this slide. Our simple mapping from ISP to the set covering problem so far does not take diversity into account. To that end, we turn to the latent representation of items. So given K from the size of the unit cost selection, we cluster the embedding space of items into K clusters and let capital K denote the cluster centers. We then reformulate the problem by changing its cost structure such that the inclusion of item I incurs a cost based on the distance to its closest cluster, and refer to this reformulation as p-diverse. In other words, we are interested in the subset of items that are far away from each other in the latent space and closer to the cluster centers. The solution is the minimum subset of items that are most spread out from each other in the embedding space, while still maintaining the guarantee that all predefined labels are covered. While solving the first 2 steps successively leads to the smallest, most diverse set with coverage guarantees, it provides no control on the cardinality of the selection. We select up to T items from the diverse selection such that the coverage is maximized. In this formulation, called P max cover at T, the objective is to maximize the number of unique labels covered. The first constraint limits the total number of selected items with a given upper bound T. The second constraint links the selection variables xi with the label coverage variable and states that if a selected item exhibits the label, then that label is covered. The third constraint ensures that if a label is covered, at least one item offering it should be in the selection. Bringing these components together, this algorithm depicts our multi-level optimization framework that consists of solving P unicost, P diverse, and P max cover at T. Notice that the framework is flexible to accommodate different latent text embeddings, clustering techniques, and distance metrics that fit a given data set the best. A concrete instantiation that we use in the paper is a term frequency featurization of item descriptions with a standard k-means clustering algorithm and cosine distance as the distance metric. Given the solution of ISP, the experimentation phase can start. This yields the training data, which is used to build a personalization model. And as mentioned earlier, we then also propose a simple warm start procedure to warm start items that were not included in the experimentation phase. The warm start procedure broadly consists of first calculating the item-to-item similarities using the item embedding, then finding a distance threshold W based on similarities of all items in S. And given distances, the pairwise distances, we find the closest item S for each untrained item S prime, such that the distance between the pair is smaller than our threshold W, ensuring that the two items are sufficiently similar. Lastly, we use the training data or trained parameters of the model to warm start S prime. Now that I've covered the problem definition and the two main components, I'll hand over to Xin to present some of the experiments we performed to evaluate our approach.
Thank you, Bernard. So this is Xin. I'm going to introduce the experiments. To demonstrate the potential speed up in random experimentation and effectiveness of the warm start procedure, we consider the following specific questions. First, what's the minimum number of items required to cover all labels? Second, how much speed up is enabled in the exploration phase when using optimized item selection to collect the response data for training? Third, how effective is the warm start procedure in increasing the number of items and the resulting coverage? And the last one is, how sensitive is the ISP to the choice of latent embedding space of items? At the beginning, let me introduce the data we used in the experiments. We used two well-known data sets from the recommender systems literatures. The first data set is Goodreads data set, which is for the book reviews recommendations. And this data set has more than 11,000 books. And the second data set is Movie Lens data set for movie recommendations. The data has more than 62,000 movies, and we consider two randomly selected subsets with 1,000 and 10,000 items respectively. And we use an open source package called Python MIP to solve the proposed optimization problem. And the table in the bottom is showing you the predefined categories for both of the two data sets. And for the different data sizes, we have different number of labels to cover. So in the experiments, we compare our method with several other methods. The first method that we compared with is the random method. So we use the uniform random selection as a simple baseline. The random method uses the subset size K from the solution for solving the p-unit cost problem. And the second method we compared with is based on a greedy strategy. So the classical greedy heuristic for set covering that as items iteratively is used, and where at each step, the item with the best ratio with the cost over coverage is selected. And we also compared with the method based on k-means clustering. So we clusters the latent embedding space into k centers and then selects items closest to the centroids, independent of the item labels. So the first question that we want to answer is, what's the minimum number of items required to cover all labels? And the following table is showing you the results. So we can see that by solving the p-unit cost problem, we can find the minimum number of items required. And we see that p-unit cost yields substantial reduction in number of items. And we also see that the coverage from random and the k-means methods are markedly lower for the same number of items. And we observed that the greedy method didn't always yield the optimal solution, meaning that greedy method might still be able to reach 100% coverage, but it would require more items. And the second question is that how much speed up is enabled in exploration phase when using ISP algorithm? And the following figure is showing you the speed up. And the y-axis is for the coverage percentage. The x-axis is for the required number of items. And the solid lines are the coverages before we do the warm start. And the dashed lines are the results after we do the warm start. So as you can see, for a given coverage, the required number of items is lower for the max cover method compared to the other methods. And after warm start, the coverage for the max cover method continues to rank the highest. The third question is that how effective is the warm start procedure in increasing items and coverage? And the following figure is showing the effectiveness of our method. So y-axis is for the coverage per item, and x-axis is for the distance quantile parameter, which is used to control the number of successful warm starts. And as you can see, when the distance quantile parameter is increased, the coverage per item decreases for all the methods. And consistent with the coverage analysis, the max cover method is the most effective approach in terms of the number of labels covered per item. And it's significantly better than the random and k-means method, especially for the top decile. The last question is that how sensitive is the ISP algorithm to the choice of latent embedding space of items? So the following table is showing you the results. And here we are showing the results on the Goodreads dataset, and we calculate the coverage per item after solving the max cover method. And in this table, we compare the results from 4 different embedding methods, and we see the similar unit coverage can be achieved for the different embedding methods. And in general, more complex methods appear to provide better unit coverage compared to the TF-IDF method, which is based on the term frequencies. Besides the experimentation, we also think that the selection of items is not purely an algorithmic problem. There are other criteria beyond coverage and diversity, such as the user preferences, legal constraints, or the time-sensitive information. So the entire process could be a human-in-the-loop optimization problem. For that purpose, we build a analysis tool. For conclusion, in this talk, we have introduced one of our works on optimized item selection to boost exploration for recommender systems. And we have introduced a algorithm, ISP, which is used to solve the proposed problem. And we introduced a warm start procedure. So here is a list of the other publications and open source softwares from our group. So we are from AI Center of Excellence at Fidelity. Thank you.
Okay, thank you for the very interesting talk. We are running out of time. Are there any questions?
Yes, there's a question in the room.
Okay.
Yes, thank you for your presentation. So I have just a question for this comparison with the greedy set covering heuristics. So what do you think if you use more sophisticated heuristic for set covering? How would your approach compare to it?
You need to unmute. You need to unmute.
So hi, so this is Xin. So yeah, so in our experiments, we just compared with the greedy heuristic method. So, but the greedy method, the greedy method neglects the kind of diversity, and so I think, I mean, if we haven't kind of compared like more sophisticated methods other than the greedy method. So I guess we can compare like the more sophisticated algorithms in the future like works.
Okay, thank you.
Any more questions?
Not from us.
Okay, so if not, I would like to thank all the speakers of the session, and I will close the session. Thank you very much.